Hi everyone. I hope you had a nice night. So welcome to the second day of this spring school. And today we have three lecturers, two of which already talked yesterday. So welcome them again. And the so our first speaker is Frank Schindler from Imperial College, London. So let's welcome him. So he's gonna talk about the introduction to topological band theory continued. Let's welcome.
Thank you. Okay, so let's just start right where we left it off yesterday. And I realized that at the last thing I wanted to show you yesterday, everything was going a bit fast. So I kind of want to do it again more slowly this morning before we go on. But just to recall, what we showed yesterday was, for example, this Z2 classification in 1D, and that is due to only particle-hole symmetry. So the idea was that particle-hole maps a state at energy E to a state at energy minus E, meaning that states at a finite energy that's non-zero, E equal non-zero, should always come in pairs, meaning that a single state at equal 0 cannot split away from 0 because it's not a pair, it's just a single state. It would have to have a partner in order to go to some finite energy. So that's topologically protected. But two states can move away, that's fine. One state is mapped to the other by particle-hole symmetry if they move away. And so that's why we get a Z2 classification. A single state is non-trivial, two are trivial, and that's the property of this group Z2. And in Z2, there's a single non-trivial element, let's call it 1, and 1 plus 1 is 0, the trivial element in Z2. And then we looked at this other symmetry class, A3, up here, where we have a chiral symmetry instead of a particle-hole symmetry. And the chiral symmetry is pretty similar to particle-hole in that it maps states at energy E to states at energy minus E, but the difference is that it's unitary instead of anti-unitary. And that gave us a Z classification. And I just wanted to quickly rederive that because I was going a bit fast at the end of last lecture. So when we look at like what we wrote down last time, we had this relationship, right? Chiral symmetry anti-commutes with the Hamiltonian. So we have this relationship, which means that CH is minus HC. And that way we were able to show that if H psi is some eigenstate, E psi, that means that H C psi, if you view that as one state, is equal to minus E C psi. So you could call that psi prime, for example. That is psi prime. And that's just the eigenvalue equation for some other state psi prime that has energy minus E. Now, if E is 0, then we could choose psi prime to be just equal to psi, up to a sign. Normally, this would be up to a phase factor, but we have an additional constraint, which is that c squared is equal to 1, which means that the only two possible choices, right? What this is saying is c psi is basically satisfying this eigenvalue equation for c, meaning that c has an eigenstate psi, and the eigenvalues have to square to 1, so the only possible choice for the eigenvalues is plus or minus 1. So that's important, it's not just any phase. And that's what is different about chiral symmetry, because we can define an eigenvalue for chiral symmetry, because it's unitary. For an anti-unitary symmetry, you run into the problem. Let's just try this just to illustrate this. Let's say we have this anti-unitary particle-hole symmetry from before. So we have this equation P psi is equal to some lambda psi, where lambda is an as of yet undefined eigenvalue. The problem with that equation is that if you now do a generic phase shift, so for instance, I could multiply my states psi by a phase e to the I alpha, that should be allowed. Like quantum mechanics is invariant under these kind of phase shifts or gauge transformations. But now, because P is anti-unitary, if I want to move this out, I'll get e to the minus I alpha P psi, which is equal to e to the minus I alpha lambda psi, right? Which means we've managed to change the eigenvalue lambda to an eigenvalue e to the minus I alpha times lambda. So the eigenvalue is not well defined. We can't actually write down an eigenvalue for this anti-unitary symmetry. So eigenvalue is ill-defined. Okay, so that's just a little interlude showing you that we can't do that for particle hole symmetry, which is why eventually we'll get a Z2 classification for particle hole. But now let's carry on for chiral symmetry. So say I have some spectrum at the edge of a one-dimensional system, and we said yesterday that's a zero-dimensional spectrum, so there's no momentum left. And let's say I have these two zero modes. Let's call them 1 and 2. Yes. Yes.
Choose psi prime to be plus or minus psi.
Right.
But we don't have to.
We don't, well, if there's only a single psi, right, like meaning only a single zero mode, then we see that from this equation that C psi is also a zero mode, right? But we know since there's only a single state that that has to be equal to the same state, meaning the state must be an eigenstate of C.
Why are we saying that there's only one state?
That's just the assumption. So I'm saying if we have a single state, then this must be an eigenstate. But you're right, if you have many degenerate states at zero, then we have to first diagonalize the chiral operator in that basis. But that's always possible because the chiral operator in that, like it leaves the basis of zero energy states invariant, right? Because of this property. Whenever you have a state that's zero energy, the chiral operator acting on it is still a zero energy state. So the chiral operator is some unitary matrix within that Hilbert space of zero energy states. So we can always diagonalize it and then we get the eigenstates. Okay, any other questions before we move on? Okay, so let's say we have these two zero modes now. And with just particle hole symmetry, we saw that that is trivial because now we can move them out, right? So we might naively want to say, well, we can go from this situation to a situation where we have these two states, 1 and 2 here. And really, these could be some different choice of states, but let's just call them 1 and 2. They are two different states. And what we have in that situation is C psi 1, right? We've seen that C for a finite energy state flips the energy e to minus e. So we can choose C psi 1 to be equal to psi 2. In principle, there's a phase factor here, but we can choose that without loss of generality to be 1. And then likewise, because C squared is plus 1, we then have C psi 2 is equal to psi 1. So in that situation where the states go off to some finite energy plus E minus E, we have the situation that C maps between the two states, meaning that if we write C in the basis of these states, so I'm going to write this matrix element psi alpha C psi beta, and that is some general matrix element where alpha beta is 1 or 2, then I'll have a Pauli matrix sigma x, basically. I'll have this matrix evaluated at the index alpha beta, right? So in that situation, C acts like a swap transformation. And that means that the trace of C in the zero energy subspace, so I should technically write something like trace, but it's going to cost a lot of space, but I'll write once, trace over 0, I'll write it like this, equal 0 of C is equal to 0. So the trace of this operator in the basis of states 1 and 2 here would have to be 0 in order for me to be able to move them away from zero energy. Right, because I know that as soon as I've moved them away to any infinitesimal E, like this E up here could be infinitesimally small, as soon as I move them away, C acts as the swap transformation, which has trace 0. But we know that trace is a basis invariant quantity that can't just change. It can't jump discontinuously as we vary parameters. So it already would have had to be 0 over here. Okay, but that means that in the other situation where we have two zero modes, 1 and 2 that satisfy C psi 1, that satisfy this eigenvalue equation from before, is equal to, for example, plus psi 1, or C psi 2 is equal to plus psi 2. Right, in that case, the trace over the zero energy subspace of C is equal to, well, C is equal to just the identity matrix in that case, right? Because it leaves both states invariant, meaning the trace is 2. So that shows you that you can never move these two states away from zero energy because the trace is non-vanishing and it can't just discontinuously change. Okay, is that argument clear, or do you have questions? Yes. Yeah. So they are just different states. There's no quantum number that distinguish. Like, I guess, do you mean the distinguishing from the case where I could move them away, or do you mean between the two different states that are zero energy modes?
It feels like there's two states that have all the same numbers, which
right.
feels like Violet Pauli. So
no, it's like just a two-dimensional Hilbert space. Like take a spin system where the Hamiltonian is 0, right? Then again, there's nothing that distinguishes these two states. You could like you could come up with some artificial distinction, but it's not really important. It's just a two-dimensional Hilbert space. Yeah. Right, so it doesn't violate Pauli. Like, remember that everything we're doing is single particle non-interacting physics here. We haven't yet filled particles into these states. But even if you did that and you did some second quantized picture where you occupy these states, there's nothing wrong with occupying two orbitals of the same atom, for example. One could be an s orbital, one could be a p orbital or something. Or it could be, you don't even need, like the notion of s orbitals and p orbitals presupposes some symmetry, but you could have broken that symmetry and then it could be two slots. Yeah. Okay, any other, yes. Right, so very good question. So in that case, let's say you have that situation, right? So where you have these states 1 and 2, and then C psi 1. I guess what you mean by parity is the eigenvalue of C, right? Is plus psi 1, and C psi 2 is minus psi 2, right? So that's another option. In that case, the trace of C is equal to 0. So now they can be moved apart. So the topological invariant in that case is the trace of C. But we know that the trace of C in that state, because C always has eigenvalues plus 1 or minus 1. So that trace of C in the zero energy subspace is always going to be some integer, right? Let me, is that a good sound? Like that? So it's always going to be some integer. So that's exactly the Z classification. Like this quantity differentiates an integer number of different. So any integer will give us a different phase because it will have a different number of edge states. Yeah. Okay. Yes. Yeah. Right. Right. That is another way to do it. I mean, you see these are consistent with each other. Yeah. So that means you could move it away. So you could have already moved it away and then computed the trace. Yeah. Okay. So just to like look up here, so that shows the Z. That shows the Z classification because this trace of the chiral symmetry is any integer. And as long as it's different, say you have trace equal n and then another system where the trace is different, some n prime, then these two systems cannot ever be adiabatically deformed to one another because we've seen that we cannot move these states out of the gap and we cannot bring them in, right? So that the converse is also true. If you wanted to bring in some states, let's say I want to add some new set of states over here, that I move in, which I'll call 3 and 4, then we know that those states have trace 0 because they are mapped to each other by chiral symmetry. So they also can't change this integer. Of course, you could always do that to add some accidental states at 0 energy, but these are only like accidental, they are not protected. So they are not part of the protected gapless states that are described by the bulk boundary correspondence. That's basically just a fine-tuned model then that has some spurious extra 0 energy states. Okay, so that's the last bit on the 1D. So please ask any questions if you still have questions on 1D, or otherwise we'll go to 2D. Yes?
Yeah, so the way I understood what you said is you have a trace for C and that can be in volume
Yeah.
phases correspond to C. Does that mean that you know, I have this last case for C is basically like poly Z, and the early case where it's like poly X. Obviously, there's
Yeah, like identity instead of, or you mean this very last is poly Z, right?
Yeah. So I guess how can I convince myself that, you know, really the trace is the thing that tells me what phase I'm in, and that if I have, you know, 2 different C's and they give me the same trace, that I know I'm going to get the same phase. That's what it sounds like.
So if you have 2 different, sorry, what was the last bit? You have 2 different C's?
So, it sounds like I get a trace for C at the end.
Yeah.
And that has some integer value. And it sounds like that integer value is what tells me what phase I'm in.
Yeah.
So I have 2 different C's and they both give me the same integer value. How can I convince myself really that those should be in the same phase? You know, in this accepting classification.
Right, because you can show that there's in this kind of 0-dimensional spectrum, right? There's no other protected quantity. So you could think about what else could you read off from that spectrum that's universal, and you could try to convince yourself by that by just adding some states. Just add some, like bringing in these 2 states that are red here. You see that doesn't change the trace. And if you take any 2 systems that have the same trace of C, that means they have the same number of protected 0 energy states there. But that's the only thing that's protected in the spectrum. Like there's nothing, everything else you can move states around by just local potentials. You can shift their energies wherever you want them to be. Yeah, so I guess the question is, it's more like the onus is on you to tell me what else should differentiate these 2 systems in that case, if this trace of C is equal. And I think in this case, it's pretty, like maybe you have to think about it for half an hour or so probably, to convince yourselves that there's really no other quantity we could write down. But yeah, it's a bit non-trivial. Yeah. So, yes.
I have a question. So regarding the bulk boundary correspondence of this 3 classification, is it associated with some like very phase like thing in the 1D bulk?
Yes. So it's associated with the winding number in the 1D bulk.
So is it the ZAP phase?
So in the ZAC phase is only Z2. So it only captures this number mod 2. But the winding number captures this number. So if you want, I can just quickly write down the equation. So the winding number, which is defined for the 1-dimensional bulk Hamiltonian, right? Is given by 1 over 2 pi integral over dk from 0 to 2 pi of this derivative d by dk log that h of k, right? Where this is now the 1D bulk Hamiltonian. So you can show that that is actually equal to trace of equal 0 C. So that's the bulk boundary correspondence. We have a bulk quantity that is quantized and that is equal to the boundary quantity. But I don't have time to derive this. This is a bit too fast.
Oh,
yeah.
That's fine.
Yeah. Okay. 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 Yes. Yeah. Yes. Then you choose the convention where you don't resolve the sublattice positions. Yeah. Right. So the winding number has this problem that you can't introduce the V matrix. Just, yeah. Okay. Everyone happy? So 1D is over. So if you if you want to do this, I think now you have everything you need to go through these other cases. There's like a little puzzle if you want, like have a look at D3 or have a look at C2 and BD1 and see if you can rederive the Z's here and the Z2 and D3. You have everything you need. It does not go beyond what we've already done. It's just like working with the symmetries, seeing what constraints they give on the 0D spectrum, like what we've done before. Okay, so we'll move on because you know how to do that. And then the next step is 2D. And so in 2D, we're lucky because in 2D, we have this class A non-trivial Z here. Right? Like remember in 1D, this class A is trivial, but class A is the simplest symmetry class. It's the one where you don't have any symmetry. So that should be actually the most stable topological phase over here because it doesn't require any symmetry for its protection. And that's known as the Chern insulator. And it's arguably the first example, you could say, of topological insulators that was worked out in detail by Haldane in the 80s. So just for context, to give also the other phases a name, the one in class D is also known as the Kitaev chain. So the Z2 classification we had derived is exactly the Kitaev chain. If that's non-trivial, then you have a topological superconductor and you have Majorana end states, and you have all the things that Microsoft is going crazy about these days. And then class A3 here is the celebrated SSH model, which stands for Su-Schrieffer-Heger model of polyacetylene, which came up in, I guess, also the 70s, 80s to describe polyacetylene chains, but now has found its kind of its place as the hydrogen atom of topological phases because everything else can be constructed out of SSH models. Okay, but now we'll focus on the Chern insulator. So let's have a look at 2D. And we're gonna just play exactly the same game as before, which is, we'll consider the bulk boundary correspondence and derive the protected edge states. And from that, we'll deduce the topological classification. So consider a system where you have a 2D slab and you have some open boundary conditions here. So I'm gonna terminate this in one direction, but I'll basically have periodic boundary conditions still in the other direction. So this just goes on. And basically it's like in Pac-Man, if you go out here, you come back in down here. So in that situation, I still have a good momentum quantum number, right? So I can define a momentum along this direction. I cannot define a momentum along this direction. This is real space, right? Because I've implemented a boundary. And so I've lost translational symmetry in that direction. Don't have momentum anymore, but I still have translational symmetry in that vertical direction. So that means that I can plot the spectrum versus this momentum K. And I'm plotting the spectrum of the full system in open boundary conditions. So remember, the bulk is now a 2D system. So the bulk is really labeled by two momenta, which means that if I plot it as only a function of a single momentum, that means that all the other momenta that go in the x direction, they are plotted on top of one another. So it's gonna fill up and it's gonna become a pretty dense spectrum in the bulk. So the bulk is gonna be these blobs of spectra here. So this is the bulk. And we have an insulator, so the bulk is gapped as before. And now we have, in addition to these pretty dense spectra, we have, let me actually see if I can make this more dense. Maybe like this. So in addition to these pretty dense spectra, we have some edge states. And the edge states are states that are gonna not fill up because they live only on the edge. They live only over here. So they only have a single momentum. And if you give me a momentum, I can give you a single or a handful of edge states, not a thermodynamically large number of edge states, but just some handful. So the question here, and like the game becomes, again, the same game as before. We want to find a spectrum that is topologically protected, that we cannot deform to another class of spectrum. So for instance, what you could try is a spectrum like this, where let's say I have a state that goes like this, just some state that goes into the gap and goes back down. Now that state is not topologically protected, right? Because I can just push this down here by some potentials that are on the edge. And I can push it down all the way to a state that goes like this down here, and then I push it down further, and then it goes like this, and then I push it down further, and then I have gotten rid of it completely. So that state is not protected. Similarly, a state like that is not protected, right? So you can already guess what is protected, right? We've seen that the states that connect the same bands with each other are not protected. So it's a state that goes from one of the bands to the other. So now that state, that dispersion relation, I cannot get rid of because I can try to move this all the way up here, right? So when I do that, then I'll just end up with this kind of dispersion relation, but I still have a state at every energy inside the gap. And I cannot ever get rid of it. This is another of the things where you maybe have to go and sit down for yourself in peace and quiet and think about it for 10 minutes to see that there's really no way you can ever get rid of this. But let's look at the case where you have a state like that and a state like that, right? Now those two I can get rid of because I can always gap them out, right? And do a gap like that, and then get rid of everything in between, like that. So that means that I have to make sure that I take the right kind of state and that connects bulk and valence bands. It's not just any spectrum that connects them. So the one thing that's stable is if I have, for example, only right movers. So a band like that is called a right mover because when you look at the velocity, the E by dk, it's positive, it goes to the right, and then the other state would be a left mover. But if I have two right movers, for example, that's also still protected, right? There's no way to gap those out. You could think of doing a funny thing where you take that mode and try to play a game like that, right? And then you could say, oh, maybe now I can gap them out. What about this? I gap them out here, get rid of that crossing. And then I would want to get, I guess, gap them out also down here, like this, and get rid of that crossing down here as well. But you see, you still have a state, well, actually, I think I've done one thing that is not allowed, right? Right, I have to, sorry, this is of course not possible in real life. I have to gap them out like this, right? Whoop. So you see, I still have two states that cross the gap. So I haven't gotten rid of the states that connect the bulk and valence bands. And so you can play this game with any number of chiral edge modes. So these are called right movers or chiral edge modes, and the chirality this time has nothing to do with chiral symmetry. Yes?
Well, the first time you get,
yes. Mm. Yeah, so let's see what went wrong. That's actually a fun experiment. I didn't suppose I would be able to get them out like this. So see what happens here is if I did that, let's just see what happens. You see I can get a region where I don't have any states. I can actually make this smaller and smaller and smaller, right? But bands can't just terminate, right? So bands are continuous functions of the Bloch Hamiltonian. They are eigenstates of the Bloch Hamiltonian. In this case, that would be like something like, you know, trying to cut through a ball in order to make it a donut, which is some drastic change that you cannot actually realize that with any local Hamiltonian. So you can prove that a local Hamiltonian leads to a Bloch Hamiltonian that's smooth. The eigenvalues should be continuous functions of K. In this case, the eigenvalues that are inside the gap just drop, like they skip out some region, they just terminate. That's not possible. Right. Yeah, but I'm only able to get rid of it in, I'm only able to get rid of it in, right? Like, let's have a look at what happens really closely to the crossing. Whoop. Oh, I need to use the other one. I cannot get rid of it like this. I can only get rid of it like this, because that still preserves the Hilbert space. You can think of like this. Yeah, so this is a bit of a deeper argument why you can only gap things out like this. Maybe someone in the audience has a simple reason for why you can't. But the best argument I could give you is these states. You can have some U of k here. You can form a projection matrix. U alpha of k, where alpha is 1 and 2, right? These are the two states. And you can show that that projector must be smooth in a band structure that has a local Hamiltonian. And that projector would actually vanish if you gap them out the other way. Yeah. Maybe just try it. I think like probably it's easiest if you try to write down a 2x2 matrix that has these dispersions and try to gap them out and see what happens. Yeah. Yes.
So you're saying
Yes. Right, so you cannot change one into the other. That's the point. You cannot. So if you have a band, let's do the bulk spectrum that goes like this. You cannot change that ever, right? You can think of it like it's pinned to these bulk and valence bands. So you cannot pull it out. Or what will happen if you pull it out is you'll pull it down like this, but it will still be connected. So yeah, so they are different. Yes. Yes, exactly. So so we can write down some invariant, let's call it nu, which is equal to the number of right movers minus the number of left movers. And that's because any number of right movers is protected, but as soon as I put a left mover in, I can gap them out like this. And you see if I do that, I'll still end up with, let's actually do that just as a little example. Oh, I'll do it. Okay, so what happened is that you see we have two right movers still, right? And that works because before we had 3 right movers, 1 left mover, so we had 3 minus 1 is 2. And so you can always subtract them like that. So the only thing that's really invariant is this difference here that you cannot get rid of. Okay, so that's the z, right? So that is some number. That's z, some integer, which means that we've rederived this z here, which means the Chern insulator is z classified, and that's also known as the Chern number. So in the bulk, if you wanted to write down some bulk invariant, you could do that similar to up here, you know, where we wrote down this winding number. You could write down something similar in the bulk, which is called a Chern number. C. Chern number. And the expression for that is similar. It is some derivatives on the eigenstates, some integral over the full K space. But it's a bit too messy for me to explain in the space of that lecture. So let's just use the boundary spectrum to show the bulk boundary correspondence here. Yeah. Okay. Any other questions on this one? Yes.
The first one is a bit of a general question. When you were labeling the different symmetry classes in the table,
yeah.
Is there a general intuition for why some of them are superconductors and why some of them are insulators?
Oh, yeah. So generally, you know, this usually the language is that whenever you have particle hole symmetry, it's a superconductor. Because physically, the only way you could have particle hole symmetry in a condensed matter system is in this BCS theory, or like kind of BDG Hamiltonian, the mean field theory of superconductors. So that's just the language. I guess you could kind of construct some artificial fine-tuned particle hole symmetry even in an insulator, but that wouldn't be stable. that would be due to fine tuning. Yeah.
Say, if I don't have particle symmetry, does that necessarily imply it's an insulator, or could it be something else?
Right, if you don't have particle hole symmetry, well, in principle, you could apply this table even to metamaterials or to like the topological semimetals we mentioned yesterday. So it's just usually applied to insulators. But it's very general, like any system that has these symmetries. Yeah. Oh, yes.
Second question is, when you said that if I have a left moving band and a right moving band crossing at 0, then they gap out. Is there an intuitive reason for why that is not a protected condition situation?
So what is not protected? A left moving and a right moving? Right, so the intuitive reason is that when you have some state that is moving to the left and another state that's moving to the right, then you could have some perturbation that scatters you from one state into the other. And so that would not be a stable, that wouldn't be a protected edge state anymore, because scattering will give you some resistance and can make an insulator out of that. So so the point of these chiral edge modes is that they are actually perfect conductors. So when you have such a chiral edge mode here, I guess the classical example being just a single mode that goes like this, then that is a perfect conductor. There's no backscattering, there's no resistance. This has technically a perfect conductance. And that's why people are really interested in it, because it means that when you have such a topological phase, and for example, I have this 2D material, but I make a little dent in it and a little imperfection, then the edge state just doesn't care. It goes around the dent like this and just goes on its happy way. And it's like perfectly stable. Yeah. It's just very hard to realize this in an experiment. Yeah. Yes. Yeah, right. No. So in 2D, this is not the problem anymore. And there's some deep reasons for that, which have to do with linearizability. But for now, let me just say in 2D, this is not a problem, because you can see this discussion of edge states and how they wind through the Brillouin zone. It does not mention any statement about unit cells. In 1D, the difference is that you can terminate different ways and kind of generate a 0 mode at the edge for free if you terminate another way. But here, this is a statement about the global winding of the state across the Brillouin zone, and that you cannot change. Yeah. Because basically what a change of unit cell could give you is a flat band like this, right? And what you see in the 0D case, looking at a specific momentum, k equals 0, you see that is exactly another state that if I tune it the right way, I could go through 0 and then I could say this is protected. But in the 2D example, this flat band, it will gap out like this. And you still have a state that crosses the gap. You still have this band that goes all the way eventually. Okay. So that is the Z invariant of the Chern insulator. And now basically there's two options because I'm running out of time. And so I'll just give you the choice. So one option is we could look at, so that's the Chern insulator, but what we could look at is the Z2 down here in class A2, which is also known as the Z2 topological insulator, or also just colloquially the topological insulator because it's so famous. This is like the original TI. And then the other thing we could look at is we could leave the entire tenfold way behind and go to crystalline symmetries and look at something called higher order topological insulators. You decide. Who wants to see the Z2 TI? Oh, wow. It's really interesting, guys. Okay, then who wants to see the higher order TIs? Okay, so we'll go to crystalline symmetries. So the Z2 TI you can rederive pretty easily with what I've shown you. So you can just use the same kind of reasoning, look at the spectrum in the momentum space. Okay, so now, but the problem is you've kind of chosen the worst option because now it's gonna get much more technical and horrible. And we're gonna leave the beautiful arguments behind. But let's do it. Okay, so higher order TI. So the idea of higher order TI is that what we have in the Chern insulator is some model where you have an edge state that goes all the way around. But in the higher order TI, so that is something we would call first order. In the higher order TI, we have some model where you have only corner states and you don't have edge states. So here you have d dimensions in the bulk, d-1 dim gapless edge. And then over here, we have a d-2 dim gapless edge. And you can generalize that, and that's why, so that is technically an example of second order, but you could also generalize this to kth order in n dimensions, you know. But there's not so many cases. In 2D, there's only second order, and then in 3D, you have second order and third order, and that's it. So there's not so many in physical dimensions. Now the question is, how can we get that phase? That is a phase that requires crystalline symmetries. So let's have a look. So I'll draw it again here. So we have a 2D sample where you only have gapless zero energy corner states. So notice that in order to get a corner, I have to break translational symmetry in two directions, X and Y, meaning that I don't have any momentum anymore. Just like we had in 1D, we went to the zero dimensional edge. Now we go to the one dimensional boundary, which has a corner, so which does not have translational symmetry. So again, we're back to this kind of zero dimensional energy spectrum where we plot everything on top of one another, where we have the bulk states. And then let's say, in this case, I would have two corner states, right? So I need two things to protect this, right? First of all, I need chiral symmetry. Why? Because, well, if I didn't have chiral symmetry, at each corner, I could just shift the state away from zero energy, as we've seen before, right? By the way, another option would be particle hole symmetry. I'm just making a random choice. You could do particle hole, would be also a higher order. Would be more like a higher order superconductor in that case. So I need chiral symmetry, but what else do I need? So if I only have chiral symmetry, then there's a trick I can play, which is I can move this edge state all the way over here, around the corner to its partner, at which point they would be close together, right? And so I don't have this constraint of locality anymore that would prevent me from gapping them out. So if I have both of them over here, in that situation, then I have a spectrum where I could gap them out like this. So that would be trivial. Meaning that I cannot only have chiral symmetry. Now, of course, what you could tell me is like, maybe what about them having the same chiral eigenvalue, right? But there's some pretty general statements you can prove that the chiral eigenvalue of all the zero energy states in your system must always sum up to zero. So previously, we didn't consider this case because we only looked at a single edge. But also in 1D, if you look at the other edge, they always turn out to have exactly the opposite chiral eigenvalues. And you can prove that on general grounds. So these have opposite chiral eigenvalues. So there's nothing in principle that prevents me from moving this edge mode all the way around the edge and gapping it out. And that could be done by some local perturbations that do not close the bulk gap because it's only happening on the edge and they don't break any symmetry so far. It's perfectly compatible with chiral symmetry because they have opposite chiral eigenvalues. So I need a spatial symmetry. And the classical symmetry that we use, like the canonical thing, is inversion symmetry. But you could have a couple other choices as well. But the simplest one is inversion, which maps x to minus x. Right, so what inversion is doing is, if I have a state like that and a state like that, then they are always mapped to each other by inversion symmetry. They are always on opposite ends, meaning that if I wanted to move this down here now, I would at the same time move this other state up here, right? These are the states I move to. And so I can never get them together and gap them out with each other. They are always on opposite ends. So that means that now I have a protected face and I cannot ever get rid of these edge states, these corner states. And so this goes beyond the tenfold way because inversion symmetry is a spatial symmetry. It maps x to minus x. It's not any symmetry that is acting local, like particle or chiral symmetry or time reversal. Okay, do you have questions on that argument? Yeah, you could have any because you see I can move them around like this. So all of these are adiabatically connected to each other. That's not a topological distinction. So it's going to be some, usually it happens at the corners for energetic reasons because they like to sit at the corners, but you can always cook up a model where they don't. Right, so the problem is if you have 4 with only inversion symmetry, then I could move those 2 like that. And then I could move them all the way here, at which point I could gap them out in pairs again. So only 2 are protected. So you see it's a Z2, exactly. So that's a great question because you see it's a Z2 classification. So we've derived a new element of this crystalline beyond tenfold way. It's actually a really large table. So there's papers that worked out this classification and it goes well beyond tenfold. And you can have a look. For example, Shiozaki and Sato have worked this out. But it's really quite extensive. Okay, there was a question. Yeah, so that would be fine. You can have that if I have a circle, then you just need to choose 2 positions where you have these 0-dimensional states that are opposite of one another. There's nothing topological about the corners. Yeah. Yes. So if in a circle, don't you restore angular translational invariance? Yeah, so you can use them in a circle. I think you will have to break that somehow, but that is always possible with an inversion symmetric term. So if you consider a generic Hamiltonian, you will have these terms present and they will break the rotation symmetry. Yeah.
Is it stable or not?
Right. No, this is stable as long as you preserve inversion and chiral symmetry. You cannot ever get rid of these. Yeah, even if I think what happens if you restore the full angular symmetry, you'll get states that are spread out across the whole circle, but they will be orthogonal and you can't gap them out. Yeah, they will have opposite inversion eigenvalues. So inversion will be the symmetry that prevents you from writing down a perturbation that gaps them out. Yes, it's just important that you have open boundary conditions in the 2 directions. Yeah. Okay. Any other questions? So we have, yes. Sorry? No. You don't need a lattice. You could do this in the continuum. Yeah, you just need inversion and chiral symmetry. Yeah. Okay, so what about the time? 12 minutes. 10 minutes. Okay, that's great. Okay, yes. Yeah. They can. That's why chiral is not enough. We need inversion symmetry. Yeah, that's exactly the reason why we need a spatial symmetry to protect that. Right, but if you have inversion only, then I could always locally just push them away, for example, like that in the same direction. You're right that there's a notion of filling anomaly that was mentioned yesterday in Maya's talk, for example, where you can still come up with some topological protection even in this case, but it's just a little bit technical, and so I didn't want to mention it. Yeah. Yes.
Without the symmetry, can't there be something else that stops them from talking about? I don't know what technically counts as a system.
Yeah.
Since you said that's to something.
Yeah.
But if there was just some separation between the upper and lower half, then you couldn't put them across the bound.
Yeah, but the problem with that is, so if you have a separation, right? So I'm going to split it up like this, right? So what happens in that case is you're basically generating two systems, right? Because they are separated, and then they will have corner states like that. And so you still haven't gotten rid of the corner states. But now you have the same problem that you could move, if you don't have the symmetry, you can move them around again individually on either half and gap them out. So you always need the symmetry. Yeah. Okay. So if I have 8 minutes left or so, I can do, so one option now would be to call it a day and stop it while it's, you know, like stop it when it's still good. But the other option is to go all in and do a horrible technical argument. So since I still have time, I'm gonna do the horrible technical argument, just so that you get a flavor of what's happening. So we're gonna show how to construct a higher order TI from two churn insulators. So the trick is, if you have two churn insulators, churn number one, and I'm gonna add to that. And the fun thing with topological phases is you can always add them and subtract them like Lego pieces, basically. You're gonna get a system that consists of these two stacks. So a stack of two phases, one is churn number one is churn number -1. And I'm gonna add to that chiral symmetry. And I'm gonna add to that inversion symmetry. And that is gonna be a 2D second order TI. So why is that? When you look at the edge of the system with two churn insulators, well, one is churn number one, right? So it's gonna have an edge state like that, a chiral edge mode goes like that. And the other is churn number -1, right? So opposite churn numbers must have edge states that go in opposite directions so that they can gap out, right? Because we know that 1 and -1 should be no churn insulator, so no chiral edge state. And now I can look at the system where I'll do it like that. So I still have momentum in that direction, and I'll have this crossing at either edge, right? Because in the bulk, I really have a coupled system of churn number 1 and -1. So at either edge, I get these crossings. Now locally, these crossings are described by a Hamiltonian that goes like K times sigma-3, where sigma-3 is the Pauli matrix 1, 0, 0, -1, right? Sorry?
The last figure?
Yes.
What's that set up?
So that is like a 2D system here in the bulk that has two edges. One edge up here with a chiral edge state and an anti-chiral, so like left mover, right mover, because you have the two churn numbers. And also a bottom edge where you have these two. Right, so now I want to write down a Hamiltonian on either edge. And over here, I have a Hamiltonian that's just K times sigma-3, Pauli matrix 3, right? Because one goes like K, the other goes like -K. So if I want to write, so let's call that H tilde. If I want to write the full Hamiltonian H, I'll have to write down the symmetry representations. So chiral symmetry, I can fix to be, without loss of generality, I'll fix it to tau 0, sigma-1, where tau is the matrix maps between A and B. So that's some other Pauli matrix. That is A, that is HB. So tau 0 just means it's the same on either edge, which it should be because chiral symmetry is local. So it doesn't care about positions in real space. So the tau, which is the distinction between A and B, shouldn't matter. So tau 0 is just the identity, right? And then inversion symmetry should map between the two edges. So inversion symmetry should be a tau 1, right? Because tau 1 is the Pauli matrix that maps. And these kind of matrix products you should understand as a Kronecker product. They act in their different spaces. The tau acts on the edge degree of freedom, and the sigma acts on the degree of freedom on each edge. So inversion should be a tau 1. Sigma-3 And the reason that it's sigma 3 is it has to anticommute with chiral symmetry, because we've seen that the two corner states that are related to each other by inversion have opposite chiral eigenvalues. So I better choose an inversion symmetry that anticommutes with chiral symmetry. Okay, so my Hamiltonian now has to be symmetric under inversion. So if I have a K here and I have a sigma 3 from before, I better choose a tau 3, because it should anticommute with inversion, because inversion takes K to minus K, right? Inversion sends K to minus K, so it has to anticommute with this term. And I'm not allowed to write something like tau 2, because that would map the two edges to one another, and I should have a local Hamiltonian. I shouldn't have any coupling in the Hamiltonian that couples between the two edges. So I can only write something like tau 3. So the basic question we have, this is a Dirac Hamiltonian. What this Hamiltonian describes is a system where you have these two crossings on either side. And the basic question is, can we write down a mass term that gaps out the crossing? Right? We should be able to write down a mass term, because we know two Chern insulators are trivial if they have opposite Chern numbers. A mass term in the Dirac equation, and this is something I don't have the time to derive, but if you look at the Dirac equation, maybe look at these matrices, you'll find out that it has to anticommute with the kinetic term in order to open a gap. So we want to write down a matrix that anticommutes with the kinetic term, commutes with inversion symmetry, and anticommutes with chiral symmetry, because it needs to preserve chiral. And then the only option is, and you have to trust me on this and just work it out in peace and quiet, see that all the other options fail for some reason, is tau 2. Oh, wait, actually, sorry, it has to be tau 3, because I shouldn't allow myself a non-local term. And now we want to anticommute with the kinetic term, commute with inversion. So it's better be something like tau 3 sigma 2, right? Because it has to anticommute with chiral. So this term anticommutes but also anticommutes with chiral and commutes with inversion, right? So that is something you just have to look at and figure out. There's no other Pauli matrix combination of taus and sigmas that you could write down that satisfies all of these properties. This is the only choice. And now we are done, because now we can look at this and see there's a tau 3 here. So tau 3 means 1, 0, 0, minus 1, right? So it has an opposite sign on the two sides, meaning that the mass term, well, it has opposite sign. If I now do this into a full, make this into a full 2D system, here I have some mass, but over here I have minus that mass, right? Because it has the opposite sign, meaning the mass has to go through 0 at some point in order to go from one side to the other. So let's say it goes through 0 here, and then by inversion symmetry, it has to go through 0 over here. But we've seen that if the mass goes through 0, we still have a gapless state. And so that's our corner states, and we're done. Okay. Do we have time for questions, or should we just maybe do it in a break?
Maybe one.
Okay, so we have a little bit of time. Yes. Oh, yeah. In a 2D, exactly. That's. So it would be the Chern number, but you're asking, can I define something that captures the higher order phase, right? Yes. So you can also do that. It's going to be a more complicated invariant. Yeah. Right. Yes. Right. So you would have to introduce time reversal symmetry to go to the TI phase, because TI requires time reversal. So you have to increase the symmetry. Like a higher order TI with time reversal symmetry becomes a TI, and vice versa. Yeah. Okay, yes. Because we want, if you look at we've seen chiral symmetry can be used to define eigenvalues. So this could be chiral eigenvalue 1. And you can show that the chiral eigenvalues must always sum up to 0. Because basically the trace of chiral symmetry has to be 0, otherwise you would get a gapless bulk. You can show you get this flat band in the bulk that's at 0 energy. So trace of chiral symmetry must be 0. And so chiral has to anticommute with inversion because inversion flips the two states. It goes from one corner to the other, and so it should flip also the chiral eigenvalue. Yeah. Okay. Great.
Okay, let's thank the speaker again. And this afternoon, so we can talk later.